So, hello everyone. I'm Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So, we will be going over the contents of week 9 and few contents from week 8. We'll discuss the questions of the assignment and we'll conclude. So, we'll begin with. So, static stability is what we had discussed in the previous weeks up to week 7. What it concludes is that these are the three conditions necessary for stability, for static stability. Longitudinal stability, you have Cm alpha should be less than 0. For lateral, for directional stability, you need Cn beta to be greater than 0. And for lateral stability, you need Cl beta to be less than 0. Okay. What are the major contributors towards these terms? Cm alpha, the major contributor that contributes towards stability in the longitudinal sense is the horizontal tail. For the directional stability, it is the vertical tail with the rudder, horizontal tail with the elevator. And for CL beta, that is lateral stability, you have all of these components, vertical tail, high wing, and dihedral angle. So somebody had asked in the previous class how low wing is not stable and how high wing is stable in the lateral sense. So if you have an aircraft here and it's a high wing configuration, okay? So when it banks, it is encountered by the oncoming velocity here, and it produces a restoring moment, okay? So it is stable. Similarly, if it is for a low wing, you have this and same banking, same rolling, the oncoming velocity hits here and you have a further deteriorating moment. There is no restoring moment. So low wing is not stable for the lateral sense. High wing is stable for the lateral sense. How do you make the low wing configuration more stable? You introduce a dihedral angle. So original wing was like this. You introduce a dihedral angle. So like sir had derived in the class, the dihedral angle contributes towards lateral stability, okay? So this concludes your static stability in the longitudinal, directional, and lateral sense. We then began with dynamic stability when we began with point mass system. In a point mass system in a two-dimensional XY coordinate system, okay? So the 4 equations of motion that govern this point mass system are given here. So you have V dot equation, gamma dot. Gamma dot is the flight path angle. So if your point mass is moving with an angle with respect to local horizontal, that is your gamma. Rate of change of this flight path angle is gamma dot. We have V dot equation, gamma dot equation, and the translational velocities, that is X dot and Y dot. So how it moves in the X direction, how it moves in the Y direction, okay? So these are the 4 equations of motion that govern the motion of a point mass system. Okay, how the velocity changes, how the flight path angle changes, and how it changes in the translational direction, that is X and Y. So for dynamic stability, this was a point mass. So when you move on to an aircraft, you have the aerodynamic parameters CL, CD, CM, such, okay? So we have assumed CL, the linear assumption, the linear expansion for the CL was CL naught plus CL alpha into alpha. So it was this term and the control term. Delta E is the elevator deflection and the elevator is the control surface. So this is the control term and this was the original term that we used, okay? So these were the 2 terms that we had utilized throughout the past few weeks for static longitudinal stability. Now when dynamic stability comes into picture, what comes is time. The time component comes into picture. When the time component comes into picture, you have parameters such as Q and alpha dot. What is Q? Q is the pitch rate. What is alpha dot? Rate of change of angle of attack. Okay. So now we would have traditionally written CLQ into Q. Okay. We would have written like this. But since now CL naught is dimensionless, this entire term, alpha is dimensionless, delta E is dimensionless. So they are in radians, but they are dimensionless. Okay. So since they are dimensionless, even these 2 terms have to be dimensionless to maintain the dimensional equilibrium, okay? So we could not use this term. What we use instead is we non-dimensionalize the Q. Q is radian per second. That is the pitch rate of change of the pitch of the aircraft, okay? So how you pitch the aircraft, how much it changes per second. So radian per second. Q and alpha dot both are radian per second. Now how do you non-dimensionalize it? You write QC by 2v. 2 is just a convention. You can use anything. So we are following the 2v convention. Okay. So it's QC by 2v. And here the CLQ. CLQ is what? It's dou CL by dou QC upon 2v. Okay. So it's not just dou CL by dou Q. It's dou CL upon dou Q by QC by 2v. So the physical significance of these terms remain the same. So it is the rate of change of CL with respect to Q. We are just introducing the other terms to make sure that it is non-dimensional, that you have non-dimensional terms on either side of the equation. LHS and RHS have non-dimensional terms. Similarly, we do it for alpha dot. Alpha dot, again, you multiply C and divide by 2v. Again, CL alpha dot is dou CL upon dou alpha dot C by 2v. Okay, so that is your derivative. Those are your derivatives. Similarly, we do it for the pitching moment. Cm, initially we had taken only Cm naught plus Cm alpha into alpha plus Cm delta E into delta E, which is the control term. Okay, control. Okay. Again, we introduce those two terms, that is variation of pitching moment with pitch rate and with rate of change of angle of attack. That is with Q and with alpha dot. So again, you have these two new terms similar to the CL term. Okay. Okay. So now what happens when you pitch the aircraft, when the aircraft is subjected to a pitch rate, when the aircraft is changing the theta? So there is a Q. Okay. So there's a radian per second component. What are the changes that are seen in the aircraft? There is a change in the angle of attack at the tail, right? So this is delta alpha tail. So when the aircraft was initially, so this is the fuselage reference line and it pitches up. So this was the tail, horizontal tail. So there is a change in the angle of attack at the tail, right? So delta alpha t, how much it changes? Approximately it is QLT by V. Q is the pitch rate, LT is the momentum between the CG and the AC of the tail. Okay, that is LT. And V is the velocity. So approximately the change in angle of attack at the tail is QLT by V. Now when the tail witnesses a change, when tail witnesses an increase in the angle of attack, what happens? There is a lift component. There is an increase in lift. So when your tail is put down, there is an upward. So if your tail goes down, that is how there's an increase in angle of attack, right? So there's an alpha tail here. There is a delta. So this is delta alpha tail and there's a delta L due to this delta alpha tail. That is given by this equation. Similarly, because of the delta lift, there is a pitching moment. So this delta L produces a nose down pitching moment about the CG. Okay, so which is why you have a negative sign here. This is the delta M due to the change in angle of attack at the tail. Why is there a change in angle of attack at the tail? Because you have introduced a pitch rate. You are pitching up the aircraft, pitching up or pitching down, you're changing the angle of attack. So the change in the lift, the positive change in the lift produces a negative pitching moment at the CG, which is why you have a negative sign. Now its derivatives CLQ and CMQ are given such. The CMQ again has a negative component. The reasons we have just discussed now. Now if we compare it to a second order system, we take a regular spring mass damper system. So that is your mx double dot, x dot and kx. Okay, if you compare it to this system, what are the terms that are analogous? Okay, so your states here, in the state in the spring mass damper are x and x dot, right? So the states in this case would be alpha and q. So alpha and q. Okay, alpha dot is similar to q, so alpha and q. These are your two states. That is analogous to x and x dot. So the coefficients that are analogous in both cases would be Cm alpha. We have studied previously. It is the stiffness. So it is how much it resists the change, the tendency of the aircraft to go back to its equilibrium when subject to a perturbation is what was defined as static stability, right? So that is the stiffness, how much it withstands the disturbance. So Cm alpha is similar to the stiffness K, how much the spring withstands to a deviation by a pull by deviation by the mass, by the weight of the body hanging on it. That was stiffness, that was K. That is analogous to Cm alpha, how much the aircraft withstands to a change in the angle of attack. So your Cm alpha, you remember, Cm versus alpha, it was like this. Okay, you have negative. Now CMQ is where the time comes into play, damping. So when it's subject to a deviation, how it comes back to equilibrium over some time. Okay, so when you subject an aircraft to some disturbance, so it was initially at equilibrium, when you subject it to some disturbance, it goes there. And then it oscillates and comes slowly back to your equilibrium. So this is just one case. There are several ways in which it comes back to equilibrium or it doesn't come to equilibrium. If it comes back to equilibrium, it is dynamically stable. Otherwise, it is not. So this is one way in which your aircraft will come back to dynamic equilibrium. So what it measures is the damping. So this is the damped case where initially it's subject to a disturbance and it gradually oscillates back into your equilibrium position. So there are other cases like critically damped, underdamped, undamped. Undamped would be if you perturb the aircraft, it remains there. Okay, it remains, it doesn't try to come back to your equilibrium. So, critically damped is it comes back smoothly without any oscillation. So these are the various cases. So CMQ is analogous to damping. So CMQ is what tells you whether it oscillates back to equilibrium, doesn't come back to equilibrium, or glides smoothly to equilibrium. This is governed by CMQ, which is analogous to the damping in a spring system. The spring also oscillates back into its equilibrium over time. Okay, so CMQ is analogous to the damping. It's the damping factor. Now this question we had discussed previously, non-dimensional value for change in lift coefficient due to pitch rate is, I think somebody had asked a question earlier. So this is the correct option. So this is the option, the value given there was wrong. So what we had discussed in the previous class, that is right. So it is this one, so it's CLQ. So non-dimensional value for change in lift coefficient, that is CLQ. From this equation, your CL equation is there, right? Which depends on alpha Q, alpha dot, delta E. So this CLQ is your non-dimensional change in lift coefficient due to pitch rate, CLQ, which is defined as, we just defined it previously, to Q by 2V. Okay, so it should have that QC by 2V here. Okay, into, so this is a CLQ. CLQ into QC by 2V. QC by 2V must be there. Okay, that was a mistake in the one of the options of assignment 8, if I'm not wrong. Just note that. We had discussed this in the previous week. I'm just bringing it up again. Okay, so now we move on to dynamic stability. What are the forces involved and what frames we will require to analyze dynamic stability? Okay, so two frames that we require are inertial frame and body frame. Body frame because it is easy for us to measure all the quantities in the body frame. So when your aircraft is moving, the velocity, oncoming velocity in the body frame is easy. So it enables the easy measurement of various parameters in the body frame. Inertial frame is because your equations of motion, that is Newton's this one and this one. Sorry. So they depend on what? They are the differentiation, the dVc by dt, all of that are defined in the inertial frame. They're valid only in the inertial frame. So that is why you have an inertial frame. In our case, then since the time of flight and the time of analysis of dynamic stability is very short, we assume the earth fixed frame, that is XE, YE, ZE, to be an inertial frame. It is not actually an inertial frame because it is fixed with respect to earth. And when the earth rotates with an angular velocity, the frame also rotates with it. Hence, it's not an inertial frame. But for the short duration of our analysis, we can assume the earth to be, we can neglect the angular velocity of the earth, which is why we assume the earth fixed frame to be the inertial frame for our case. That is for the flight dynamic analysis of your flight, short duration analysis. Okay. Now, what are the various forces acting on your aircraft? Aerodynamic are what? By virtue of the relative velocity. Relative velocity is that oncoming velocity, the velocity with which your aircraft is flying or velocity with which the wind is hitting your aircraft. Okay. So they depend on the relative velocity and they are what? Lift, drag, such terms. Okay. Gravitational is the, the mg component, the weight component of your aircraft. Okay. Propulsive is thrust. That is the only component in the propulsive force, that is thrust. Okay, thrust on the aircraft. Now, these are the two equations of motion that define the motion of a body. That is force equation and moment equation. Force equation we had derived in the previous class, that is m dvc by dt. And now sir had mentioned the first lecture of week 9. Sir had told us how a vector behaves, how a vector is differentiated in a rotating frame. So this is the final expression. How did we arrive at that? We defined A first in inertial frame. Okay. So A is a vector. It's defined in inertial frame as AX I plus AYJ plus AZK. Similarly, the vector is same. So we can define the vector in the body frame or inertial frame. In the body frame, we define it as, let's just take small x, small ax IB plus small AYJB plus small AZ KB. Okay. Now you differentiate both of these terms. How do you differentiate dA by dt? Let's differentiate the first equation. Okay. dA by dt. So you differentiate ax. So it becomes dAx by dt I cap plus dy by dt j cap plus daz by dt k cap. Now we are also supposed to do, so it is u dv plus v du. That's the product rule, chain rule for differentiation, right? So we also have to do ax di cap by dt and so on and so forth. But this is in the inertial frame. This is the if. Okay, we are differentiating in the inertial frame. That's the first equation you are differentiating. That's the first one. So the inertial frame, we have assumed, we have taken the inertial frame to be fixed in time, right? So your di by dt, that is I, j, k, those unit vectors that define your inertial frame do not change. So di by dt will be 0. Di by dt will be 0, dj by dt will be 0, dk by dt will be 0. So your differentiation of the vector in the inertial frame would just be these three terms. Okay. Now we differentiate in the body frame. So you get dA by dt would be dAx by dt IB plus dAy by dt JB plus dAz by dt KB. And now we differentiate the unit vectors. Okay. Here in this case, it will not be 0 because your unit vectors, that is IB, JB, KB, are fixed to the body and they change when the body changes. Okay. So dIB by dt plus AY dJB by dt plus AZ dKB by dt. Okay. So now this rate of change, so if your body is rotating with an angular velocity omega, so this dIB by dt would be, so dIB by dt, we had seen this in the previous week, it would be omega cross IB, right? Similarly for JB, similarly for KB. So this final thing comes out to be dA by dt in the body frame plus omega vector cross the body frame, that vector. Okay, so you have AX into IB, so this basically becomes, this term will become AX omega cross IB, and if you take it for all those terms, it becomes omega cross A. Okay, so, and what is this? This is also equivalent to dA by dt in the inertial frame, dA by dt in the inertial frame. This is what is given in this equation. Okay, this is how we derive it. How we derive the relations. Now we use that relation in these two equations, that is F and M. So we had derived in the previous class that F is m dvc by dt. That is in the inertial frame. How do you represent it in the body frame? We do m dvc by dt in the body frame plus m omega cross vc. Okay. Similarly for the moment. Moment was m dh by dt. We converted it to the body frame by differentiating in the body frame and taking the, okay, there won't be an n here, this was wrong. There will be an omega cross h. Okay. Omega cross h comes from this component, omega cross h. That is how you represent, you equate the differentiation of vectors in inertial frame and body frame. Why are we doing this? Because in the body frame, it's easier for us to measure the various components that we would require for analysis, okay? But your equations are valid only in the inertial frame, which is why we need a relationship between the two. So now the various parameters that we use throughout this analysis are given below. That is F. F is the force. So this F, when you resolve it in your body frame, okay, so here IJK are body frame, okay, IJK from here, IJK, body frame. So when you represent it in the body frame, you have three components, that is Fx, Fy, Fz along the three axes. Similarly, for Vc, you have UVW. For omega, you have PQR. That all this is in the body frame. And we can measure all of this in the body frame, okay, which is why we're representing in the body frame, and we'll eventually convert it to inertial frame by taking that omega cross vector, omega cross whatever vector. That is what enables us to convert it into the inertial frame, okay. Similarly, you have the moment. So since there is an LMN component, I've just represented the moment vector as with a bar, okay. So the moment vector has three components in IJK. You have L, M, N. And the H vector has three components, Hx, Hy, Hz. Okay, we had derived the individual terms Hx, Hy, Hz in the previous week, that is week 8. Okay. So now we expand this Fx, Fy, Fz. How do we expand? We take, so we knew this equation, right? Using this equation, we expand it. So there will be a u dot, v dot, w dot component that comes from here. And there will be a product component between PQR, that is between PQR and VC, that is UVW. So there will be terms that are products between PQR and UVW, and there will be u dot, v dot, w dot coming from this term, okay? That is how we see it. So there is a u dot, there is a v dot, and there's a w dot, analogous, corresponding to each thing. So in x direction, you have u dot, y direction, you have v dot, z direction, you have w dot. And the product terms that come from the omega cross VC, they are given here. Okay. Now, what are these equal to? They are equal to the total sum of forces that are acting on the body. What are the forces acting on the body? You have aerodynamic factors, you have thrust, that is the propulsive factors, and the gravitational factors. We had discussed this, right? So aerodynamic, gravitational, and propulsive. Aerodynamic, gravitational, and propulsive. Propulsive is only thrust, so that is T. Similarly, you write it for this three directions. Now you write the equation for the moment equation, that is LMN components. Now let's come back to this equation. You see there is a dH by dt. So you have an Hx dot component. Hx we had derived in the previous class, terms that come from moment of inertia, Ixx, Iyy, such terms, okay? And you have an omega cross H term. Omega cross H, again you will have P, Ixx, such terms will come, okay? So here you can see. So LMN are the three components of the moment in X, Y, Z direction, that is I, J, K direction. And each of them are given, derived as these equations, okay? Okay. Now we come to Euler angles. What are Euler angles? Euler angles are a way of representation of the orientation of your aircraft, okay? They're just one of the ways in which you can represent the orientation. There are several other, I think there are a couple of other ways that you can represent the orientation. Euler angles, psi, theta, phi. And in this particular order, which is conventionally used for aircraft. You can have it in any order, but for aircrafts, we conventionally use psi, theta, phi, okay, in this order. Has to be in that order, where psi is the rotation about z-axis, theta is the rotation about y-axis, and phi is the rotation about x-axis, okay? And in this particular case, that is for our dynamic analysis case, your psi rotates about ZE. ZE is what? It's the inertial z-axis. So your aircraft, you have an aircraft here. There was an initial z-axis, x-axis, and y-axis. So when it rotates initially about the z-axis, that is what gives you your psi component. It is not yaw. Yaw is measured in the body frame. So it is measured if it's a rotation of the aircraft with respect to the z-axis of the body. That is yaw. Psi here is about the ZE. ZE is the inertial axis, inertial z-axis. Okay. So it is not yaw. Do not get confused with it. Similarly, theta is the elevation, is the elevation angle and not the pitch. Pitch is about the body y-axis. But this is about y1. What is y1? So initially you have your aircraft in this orientation. So this is ZE. And then you rotate it about ZE, you rotate for xi degrees, okay? Xi is the angle about through which you rotate the aircraft. Then you have a new x and new y, that is your x1, y1. Then when you rotate your aircraft about that new y1, that is your theta, which is elevation, okay? It is not your pitch. Pitch is with respect to body axis. This is with respect to the new y axis, okay? So do not confuse your azimuth, that is xi, with yaw, or theta with pitch. This theta is different from your pitch theta, okay? Okay. Now, where do these components come into play? They come into play in your gravitational force components, that is this part. Okay, so when you orient your aircraft with respect to the inertial frame, only place where it comes into play in the force equation is in the gravitational forces part. The other force, that is aerodynamic and thrust, that is the propulsive forces, are measured in the body frame. Okay, so you don't have this xi, theta, phi, the angles coming into play in those terms. You only have it coming in the gravitational components. How are those gravitational components? You can easily derive this. So if your aircraft is pitched, it has an elevation theta. So this x component of force, gravitational force is here, y and z component. These are the three components of your gravitational force. Okay. But they also come into play in PQR. What were PQR? PQR was omega. So previous slide we saw PQR was omega. Okay. They also come into play there. So you have PQR represented with the angles and the rate of change of these angles. Okay, so omega is the angular velocity. So there is a rate of change of those angles, which is why you have phi dot, theta dot, xi dot. Okay. These are the two places where these Euler angles come into play. Okay. So I think we'll begin with the questions. There was something else I wanted to discuss before that. Okay, yeah. So these three equations, they are the final equations. So if you take various conditions, like we were doing the analysis for steady state. Steady state means what? So these terms, there is no change with respect to time. So these dot terms, u dot, v dot, w dot, they will vanish. So steady state, you have u dot equal to 0, v dot equal to 0, and w dot equal to 0. So if you get rid of these terms, that gives you your steady state equations. The rest of the terms remain same. Then when we come to cruise condition is what? It maintains level flight, steady level flight. Okay. So your Q, R, such terms vanish. There is no pitch rate. There is no angular velocity. So those terms vanish. Okay. And then you get your original equation. What was the cruise equation? It was lift equal to weight, thrust equal to drag. Those were the equations. Okay. So you will get that. What you will get is Fax plus Ftx equal to 0. Then you get the relevant equations that we were using for the static analysis and for your aircraft performance. For these two courses, the equations that we were using, we get when we do this. Okay, so we'll move ahead with the questions. Okay, so the first question is, for the rotational matrix R given below, what are the values of xi and theta? Now, since they've not specified any order of rotation or any such thing, you assume what is the conventional thing for an aircraft. What was that? It was R is equal to, first I told you it's rotation about z axis. So Rz about xi, about z axis by an angle xi, then into Ry theta into Rx phi. Okay. So they are products. How do you get the final rotation matrix? You multiply these individual rotation matrices. Okay. Now, what are these Rx, Ry, Rz? So they are so if you rotate a body about just the z axis, you have a certain matrix that you get. I believe you know these equations. So we'll just go to the next slide. I've written them down. Yeah. So rotation about the z axis it's of this form. Cos of whatever angle you rotated about. You have sine of whatever angle you rotated about, 0. Here you have minus sine the angle, cos of the angle, 0. And you have 0, 0, 1. Similarly, you have such matrices defined for rotation about x and y. This is for Z, this is for Y, and this is for Z. Okay, they are fixed, only the angle changes. So when you rotate about Z, Y, X, you multiply 3 of them to get the final rotation matrix, that is R. Okay, this is R, I should write that. Okay, I'll just erase this because we have to solve. Okay. Now, they've asked you to find out xi and theta. Now we look at the final matrix. So this rotation matrix is given to you, and we look at the formula of the rotation matrix. Okay. So the formula of the rotation matrix, it gives you this. From this equation, what we can see, we can easily find out one angle, which is that angle theta. Right? So what we take, we equate those two matrices. We see minus sine theta equals minus 0.7071. Okay, so theta. So this is the third R31. That is the third row, first element. So theta is equal to sine inverse of R31. Is that correct? Yes, minus sine inverse, sorry. Minus sine inverse of the third row, first element. Third row, first column. Okay, 3, 1. That is how we do this. So this is third row, first column. Okay. So what happens here is this value and the pi plus this value, both of them give you the same theta. So you will have two theta values. So theta 1 is this. Okay, theta 1 is that. And theta 2, the sine value, sine theta and sine pi plus that angle, both of them give you the same sine value. So you have two possible solutions for this. So theta 2 would be pi minus theta 1. Okay, so it gives you pi plus sine inverse R31. Okay, so you have two possible solutions for this sine theta value. You have theta 1 and theta 2. Both of them give you the same sine theta value. So now let's find out the answer. What is theta 1? What is theta 2? Sine inverse of minus 0.707. Okay. What do you get? You get pi by 4. You get 45 degrees here, right? You get 45 degrees. It's minus of minus sine inverse. Okay. You get minus pi by 4. Here what do you get? Pi plus minus pi by 4. How much do you get here? You get 3 pi by, this is hanging just a minute. Okay. 3 pi by 4. Okay. So there are two values that we can obtain for the given theta, for the given sine theta. You have minus pi by 4 and you have plus pi. Plus pi by 4 and plus 3 pi by 4. Is that clear? Is there any question? Is this okay? Is this okay? Okay, so you have two possible solutions for the given sine theta value, that is plus pi by 4, this one. And 3 pi by 4. Okay. Now, how do you find, what is the next thing that they've asked you for psi? How do you find out psi? We can see that these two terms, these two, if you divide those two, you get sine xi. Okay, so if you do R, that is second row, first one, by first row, first one, you get tan xi. Okay, you can find out xi value from here. So xi equals tan inverse R21 by R11. Now what we need to be careful here is this value is dependent on your theta value. So if your theta, so if you take your quadrants, if your so if your theta is either here or here, that is if this is theta or if this is theta, then your tan theta is just directly the opposite by adjacent. Tan inverse opposite by adjacent gives you the theta. Okay, but if your angle is somewhere here, if this is your theta, and if you do opposite by adjacent, this is the angle that you get. You get pi minus theta. Even in this case, you will get pi minus theta. You won't get the theta value, right? Theta is actually this entire thing. So when your angle is in these two quadrants, this quadrant or this quadrant, you need to take the negative of that. You need to take negative. How do we check that? We check cos theta. So cos is positive in this quadrant and this quadrant, right? So if cos theta is greater than 0, then you have tan inverse R21 by R11. If cos theta is less than 0, you have tan inverse minus R21 by minus R11. Okay, so this is what you need to keep in mind. You need to check, you need to compute a value of xi depending on the value of theta, depending on the value of cos theta. Like you need to check which quadrant it lies in. Otherwise, you will get the smaller angle. You will not get the complete angle when it lies in the second and the third quadrant. Okay, so the easy way to do this is to divide this by cos theta. So you do cos theta. You divide this also by cos theta. Okay, so xi is tan inverse R21 by cos theta by R11 by cos theta. And now you have two values of theta. You have theta 1 and theta 2. So how do you find out? You put each value, theta 1 and theta 2, you will get two values of xi. Okay, so xi 1, you compute, just compute it quickly. It's R21 by R11 divided by cos theta. Cos theta you already know. R21 is 0.5 and R11 is also 0.5. Makes it convenient. Divided by cos theta 1. So it's cos 45. Okay. And tan inverse. Right? So your one value of xi is 45 degrees. That is pi by 4. And your xi 2. This is hanging. I'm sorry about this. It's slow. Okay, xi 2 you divided by, so it will be R21 by cos theta 2, R11 by cos theta 2. So you have tan inverse of that value. You get minus 135. That is minus 135 is what? 3 pi by 4. Okay, so the two values are given. Let's see which option gives you. You have for xi and theta. Xi, the two values are pi by 4 and minus 3 pi by 4. And for theta, it is pi by 4 and 3 pi by 4, which is this, the fourth option. Okay. Okay. Let's go to the next slide. Next question. Rotation matrix for the rotation about z-axis is given by r xi. What is the value of r xi into r xi transpose? So now we had written r xi as, what was the value? The matrix. Cos xi, sin xi, 0, 0. We have minus sin xi cos xi 0, 0, 0, 1. You multiply it with its transpose. So what is the transpose? So you take xi transpose. So you multiply with the transpose. You have cos xi minus sin xi 0, sin xi cos xi 0, 0, 0, 1. When you multiply this, what do you get? You get here, you get cos square xi plus sin square xi, right? So you get 1. Here you get minus sin xi cos xi plus cos xi sin xi, you get 0. This is 0. Here you get sin xi cos xi minus cos xi sin xi, you get 0. Here you get sin square xi plus cos square xi, you get 1. This is 0. This is 0, this is 0, and this is 1. So you get an identity matrix. Okay, this is true of any of those principal rotations. Principal rotations are rotations about the axis. So R, Z, R, X, R, Y, the product of them, of these principal rotations and their transposes give you an identity matrix. Okay. So the value is this one, identity matrix. So R xi into R xi transpose is always an identity matrix. The principal rotations are have this property. Gravitational force components along x, y, and z axis respectively can be written as, given that xi, theta, and phi are the Euler angles. We had studied this. It was a direct formula. Can anybody tell me which one is the right one? It was a direct formula. We just discussed this in the beginning when we were going over the concepts. Can anyone just tell me? It's just directly given. So x-axis would have a negative sign. So it's obviously one first or the third one. Then what are the other components? Let's just see. So yeah, we had fgx as minus mg sine theta, fgy as mg cos theta sine phi, and gz as mg cos theta cos phi. So that is the it is the third option, right? Third option. Can anybody tell me why this xi angle, this first angle, does not come into any of these equations? Only theta and phi are given. Why doesn't xi come into any of these equations? Can anyone tell me? I think sir had briefly gone over it, but okay, just try thinking about it. Okay, we'll go to the next question. In the following figure, XB, YB, ZB are the three axes of an aircraft body frame. XI, YI, and ZI are the three axes of the inertial frame. X dash, Y dash, Z, that should have been Z dash. Okay, that should have been Z dash. Z dash are the three axes of the intermediate frame, and V is the velocity vector. Which of these three constitute the stability axis? So I think I'd forgotten to mention this when we were going over the concepts. So stability axis, we assume we compute our stability over an axis such that our equations of motion become simplified. What is the stability axis that we have assumed to simplify our equations? It is oriented along the velocity. So velocity in this direction, in this question, is this one. So what are the axes that are oriented along the velocity? You have x dash, and when it's rotated by to x dash, you have z dash, and y dash is same as yb because you're rotating it about the y-axis. Okay, so the stability axis would be x dash, z dash, y dash. Okay, it's just an axis that we assume for our simplicity to simplify the equations. So your stability axis is oriented along the velocity vector. Velocity vector is v. So you have x dash, y dash, and z dash. Okay, so that is this one, second option. Okay, let's go to the next question. For the same question, let u, v, w be the velocity components in the stability axis. Okay, so our stability axis is x dash, y dash, z dash. Okay, so in our case, we have x dash, y dash, z dash. Then which of the following statement is correct? U, v, w are the velocity components in the stability axis. Let's go back to the image. This is the axis. So this I will just highlight it in red. this one, and y remains same. You're rotating it about the y-axis. Okay, so this is your axis. In this axis, the three components of velocity are u, v, w. This capital V is the oncoming velocity direction. Now, when you've oriented your aircraft in the oncoming velocity direction, your xb, that is, x dash points now towards the velocity. It is already oriented in the velocity direction. So it has no components in z dash and y dash, right? The entire velocity is oriented along your x dash. You have rotated your stability axis such that it is oriented with the velocity. So it has components only in the x dash direction. That is, it has only u in the other two. The other two are perpendicular to the velocity. So it has no components in those two axes. So z dash and y dash have no components of velocity. Which is that option? So here, u is non-zero, v is 0, w is 0. This is the one. Okay, so it has no components in the other axis. So u is non-zero, that is the total velocity. V is 0, w is 0. Okay. Okay. So with this, we complete the discussion of week 9. Do you have any questions? Does anyone have any questions? If not, we'll move on to the week 10 contents. Okay, I think we'll move on to week 10 if nobody has any questions. Okay, let me end this.